Okay, in this section, we are going to learn about partial derivatives. Now, my research, everything I do is a partial derivative. I absolutely love partial derivatives. They are the #1 reason why I went to graduate school, was to be able to study differential equations that have partial derivatives. So they are so cool. All right, so let's just go back to Calc 1 for 1 minute. Okay, so in Calc 1, I had a function like this, and then here is my function. It does this, and then I can choose this point right here to be some x, and I can find a tangent line to my curve at this point. If it just goes through there at one little spot. Okay, so we can talk about the slope here. So this function is y, f of x. And so y prime, well, let's say dy dx. Let me make it, let's be clear. The derivative of y with respect to x, we call f prime of x. And this, by definition for us, as we did it, is the slope of the tangent line to the curve y equal f of x at a point x. Okay, and that is so basic. We don't have a problem finding it. We say dy dx is the limit as h approaches 0 of f of x plus h minus f of x all over h. And once you learn how to do that, take the limit, life is good. Now here's the thing, in 3 space, so we're back to Calc 3 again. In 3 space, I have some function, and it may look like who knows what it looks like. Okay. But at any point xy, I can go up here, and now I can find, if I slice this thing, I can find the slope in the x direction. So if I'm on a mountain and I choose to walk north, so here is north. Actually, this should be north. This would be south. This is east. And this is west. Okay, I'm dense. Y is north. No wonder I can't draw. Y should be north. Then this would be east. Now it looks better. This is south, and this is west. I'm trying to figure out what I'm doing. But if I walk down the mountain in the north direction, I'm going to have a completely different slope than if I walk down the mountain in the east direction, because the mountain may not be completely symmetric. So it's going to make a difference whether I'm trying to find the slope in the X direction, where if I'm walking in the north direction, I'm not worried about which X I'm looking at. I'm only going in the north direction, not worried about X. Or if I'm walking in the east direction, I'm not worried about which way is happening and Y. I'm only walking in X. So that's where we get partial derivatives from. So now I want to let Z be a function of X and Y. And I want to take the derivative with respect to X. So when I take the derivative with respect to X, I'm going to hold Y fixed. And now because Z has derivatives with respect to X and Y, we have what we call partial derivatives, not total derivatives anymore, because it can be a derivative with respect to X or a derivative with respect to Y. So the symbol for the partial looks like that. So that means partial. So I'm going to take the partial of Z with respect to X. This is the limit as H approaches 0. I'm going to have F of X plus H carry Y along minus F of XY and divide by H. So this is the partial derivative of F with respect to X. Okay. Now I can do the same thing and do the partial of Z with respect to Y. So now I am going to take the limit as H approaches 0. I'm going to do F of X carrying it along, Y plus H minus F of XY and divide by H. And this is the partial derivative of F with respect to Y. Okay. Now, since Z is a function, Z is equal to F, the notation you may see, if you remember, notation from before, and let's not even do that. Let's just do it this notation right here. You might see the partial of Z with respect to X. Some people may just do the partial of F with respect to X since Z is F. Okay. You may also, oh, I want to make these equals. You may also see F sub X. Okay, so that means take the derivative of F with respect to X. You may also see capital D sub X of F of XY. And what's most not, which you more than likely will never see me write, is D1 of F of XY, where the 1 means the derivative with respect to the first argument. I never use this. Okay. You will see the partial of Z with respect to Y, or the partial of F with respect to Y. You may see F sub Y. You may see the derivative of Y of f of xy. And you may see D2, which again, you will never see me use f of xy. Because for me, D2 means something else. So you won't see that. Okay, so now the way you do this is, in order to take the derivative with respect to x, you assume that your y is like a constant. The only thing that is actually changing is x. So here's an example. So if I have f of xy is equal to 3x squared minus 2xy plus y squared. I've never done this before. I'm scared to try it. I'm actually rather scared. I've never tried
Me
this.
too.
Okay, I've never tried this before. I'm going to try to use the definition. F sub x is the limit as h approaches 0. F of x plus h, carry the y along, subtract off f of xy, and divide by h. So that is, I know what the answer is supposed to be. The limit as h approaches 0. So I'm going to get 3 times x plus h squared minus 2 times x plus h times y plus y squared. I'm going to subtract off 3x squared minus 2xy plus y squared and divide this whole thing by h. It's going to work out beautifully, just the way it's supposed to. So this is the limit as h approaches 0. In the numerator, I'm going to get 3 times x squared plus 2xh plus h squared minus 2xy minus 2y minus 2xy minus 2, wait a minute, minus 2xy minus 2hy minus 2hy plus y squared minus 3x squared plus 2xy minus y squared all over h. It's the limit as h approaches 0. So the 3x squareds are gone. The 2xy's are gone, and the y squareds are gone. Okay. So that gives me 6xh plus 6h squared minus 2hy all over y, all over h. That's the limit as h approaches 0. I'll pull the h out, and I get 6x plus 6h minus 2y all over h. And the h's divide out. And this is the limit as h approaches 0 of 6x plus 6h minus 2y. And that answer is 6x minus 2y. And that is exactly what it's supposed to be. Okay, that's exactly what it's supposed to be. So let me go back and do it the easy way. F of xy is 3x squared minus 2xy plus y squared. So when I find f sub x, I differentiate the 3x squared. That becomes 6x. Now I assume y is a constant, like 4. So it looks like minus 2 times constant times x. So anything times x, if I had minus 2 times x times 4, that would be negative 8x, and you would take the derivative and just get the negative 8. So I have negative 2 times y times x. I assume y is a constant. So when I take the derivative of a constant times x, I just get minus 2y. I just get that constant. And y squared is a constant, so the derivative of it is 0. Okay. So this okay, so f sub y, 3x squared, that is a constant because y is the variable, so x squared is the constant, it's not moving. So when I take the derivative of 3x squared, it goes to 0 because it's a constant with respect to y. The derivative of negative 2xy, well, the 2 is a constant, the x is a constant, y is just a single thing, so I just get minus 2x, and the derivative of y squared is 2y. So you hold the other variable fixed when you take the derivative. Three x cubed minus 4x squared y plus 3x y cubed. Okay. So f sub x says take the derivative with respect to x, y is a constant. Let me add on here y to the 4th. Okay, so the derivative of 3x cubed is going to be 9x squared. Now, when I take the derivative of this actually looks like negative 4y times x squared. So I'm differentiating the x squared because the y and the 4 are a constant. So that gives me negative 8xy because the y stays there. It's constant. And then you differentiate the x squared, which brings down a 2, so you get negative 8. Here, x is the only thing that's there, and it's raised to the 1 power, so everything else is a constant. So I just get 3y cubed. Oh, and that last term only has y's in it, so its derivative is 0. F sub y, well, the 3x cubed, that goes to 0. The negative 4x squared y becomes negative 4x squared. Then I differentiate the y, which gives me 9xy squared, and the derivative of this is 4y cubed. How we doing?
Good.
Good, 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 good. I'm glad to hear that. Okay, I'm gonna give you another one. This one's even trickier. F of xy is going to be the sine of xy squared. Okay. So f sub x, derivative of sine is cosine. But I got to multiply by the derivative of what's inside with respect to x, and that's just y squared. So I get y squared, the cosine of xy squared. When I take the derivative with respect to y, I get the cosine of xy squared. But
Times.
Times what?
2y.
Okay, but you still got to keep the
2yx.
2xy, yes. So you get 2xy.
The order doesn't matter because multiplication, right? So I can put
actually, order does matter. Because you don't, when you have it behind there, it looks confusing to think that you're taking the cosine of all of that's coming next. So we try to put all the other stuff in front.
No, I'm saying like, I know that goes in front, but I'm saying like 2yx the same as 2xy.
Yes, it is.
Okay.
Yeah, but we normally write our letters in alphabetical order. I was doing this with another student, and I was using A, B, and C, and oh Lord, he kept putting CAB and CBA, and I was having a hard time.
Oh no, that would have threw me off.
Because it needs to be ABC. I mean, it needs to be in the order, whether it's A, B squared, C cubed. It needs to be in the order of whatever A to its power, B to its power, and C to its power. Otherwise, I was like, this is not good. Okay, one more. This one's gonna be a little more tough. Oh, I forgot the function. F Okay, so this one's tough because it's a product rule. Okay, but it's only a product rule for one of them. Okay, so for f sub x is a function. So this is a function times another function. So I get the first times the derivative of the second, which puts x squared plus y squared in the denominator. But then the derivative of what's inside is a 2x plus the derivative of the first, which is just 1, times the second. So I get f sub x turns out to be 2x squared over x squared plus y squared plus the natural log of x squared plus y squared. But f sub y, that x is just a constant now, so it just stays there. So now I only differentiate the other piece. So the x squared plus y squared gets down here. And the derivative of what's in top is 2y. So now I get 2xy over x squared plus y squared. Okay, so notice how this one was a product rule. but the other one is not. Okay. Okay, so I'm going to try to draw this picture. And I can't use the shapes that they give me because the shapes that they give me, well, maybe I can use that. I think I can use that. Oh, that's my problem. Okay, I can use that for a minute. Okay. So I have a surface that looks like this. So here's my surface. And here's my point, X naught, Y naught, Z naught is, here's the point here. So that point is the point P naught. I don't know why I drew this so close. This has nothing to do with that. And I don't know why it does that, why it chooses some stuff to come with it and some stuff it leaves behind. I don't know why it does that, but it doesn't matter. Okay, so this is the point P naught, which is X naught, Y naught, F of X naught, Y naught. That's this point. And this surface is Z is equal to F of XY. And so now for a fixed Y naught, so if I fix Y naught, so I choose a Y, oh boy. I don't want all of that. I just want the line. Okay. Won't be difficult. Okay, so now, as you can see, there's a tangent line to the curve for a fixed Y naught. So now I can find F sub X is the slope of the tangent line to the curve Z equal to F of XY, where Y is fixed to be Y naught. So see I'm over top of Y being fixed to be Y naught at the point P in the plane of Y equals Y naught. So now basically what's happening is I have some surface, some plane that comes through at Y equals Y naught, chops the surface. When it chops the surface, it chops it into this dotted line here. And then I can draw the tangent line at that point. So here's an example what I mean. Find the slope of the tangent line to the curve of intersection Y, nope, Z is equal to 1/2 the square root of 24 minus x squared minus 2y squared with the plane y is equal to 2 at the point 2, 2 square root of 3. Okay, so I need to find z sub x. Well, that is that thing to the 1/2 power. So therefore, when I bring the 1/2 to, I have 1/2, and then I'm going to get 1/2 times 24 minus x squared minus 2y squared to the negative 1/2 power. And then I have to multiply by minus 2x, which is the derivative on the inside. So I get z sub x turns out to be negative x over 2 times the square root of 24 minus x squared minus 2y squared. So then I just evaluate that. Z sub x at the point 2, 2 square root of 3. So you get z sub x turns out to be minus 1 over 2 to the root of 3. But the tangent line, oh, I said find the slope of the tangent line. That's it. That's it. That's it. Okay, we are going to stop here because the next example will take longer than 2 minutes. And so we'll stop there.
Okay, see you tomorrow.
Okay, my dear. I'll see you tomorrow.